My name is Joseph Wunderlich. I'm a professor of engineering, architecture, and computer science. I've been involved in machine intelligence, including designing neural network chips 35 years ago, and two of them, 1991, and then went to IBM research and development and supercomputer development. And I've been a professor now for full-time, almost 3 decades. And so this is parallel processing optimization, both hardware and systems level software optimization. And this is in 2025. I've done a previous lecture with a similar name 7 years ago. It's on YouTube. I'll probably take that one down just to avoid confusion, even though there was a lot of hits and likes on that one. So this is covering dependencies, data I/O, resource and control, hardware versus software parallelism, degree of parallelism. That's a nice conceptual way of sketching out and analyzing the different ideas you have. But you really have to go down into program partition scheduling, accounting for actual timings to analyze speed up in a really quantitative way. And so we look at size of problems, grain sizes, communication delays, very important interprocessor communication, grain packing, parallel scheduling, including dynamic out-of-order execution. And speaking of communication delays, IPC, interprocessor communication, inter-core communication, the Nvidia GPUs, and the degree of how critical their communication bandwidth is, and having to do with export restrictions, controls to China at the moment here in 2025. Well, it began in 2022 with Joe Biden, but Trump has extended that, and now most recently, just the past couple of days, the H-22 as well. So speaking of dependencies and data and I/O resource and control, we want to start with an example here. Now, this is something you're probably not familiar with, but this is a tape reader, and this still is in existence for large amounts of data. I believe we do this in colleges IT. They back up everything on all the servers periodically and stored in Iron Mountain. That's a secure facility far away from the college. My wife used to do this for a publishing company every week when she was the head of an IT department, and she would bring it to a safe deposit box, a tape, every week at the end of the week. And in IBM, we did this every time we would test versions of the new supercomputers. So in the Systems 390 lab, our test floor was approximately the size of 4 basketball courts full of test machines, and right below it, with the same footprint, in the basement was a huge storage facility storing tapes from going back to probably the 1950s, at least the 1960s. You would go up to a window, and it was secure access, of course, for everything, and you would deposit or withdraw a tape, and you wouldn't go into the actual facility. There was a robot that was on tracks, and it was on like a cart, a robotic arm on a cart, and would wheel down into a certain row and then down that row and lift and go up and reach and get the tape and give it back. So anyway, that's a story telling this still exists, this kind of thing. And here's an example of dependencies here. So you see a routine here where we are reading and writing to the tape. And here, by the way, is actually a 2020 tape unit for about $10,000. So here's an example, and you're reading and writing from a tape unit, and then there's a discussion here how S1 and S3 here are I/O dependent because they're using the tape unit reading and writing from it. They'd also be data dependent if they were doing the same array. There's different arrays that are reading into each. But it'd also be a data dependent there if we were working in the same array. So these I/O or this I/O dependency here will cause some problems that I've numbered here. can cause problems. Erroneous results may be produced with a change of program order. Number 2, repetitive runs should reproduce identical results. Number 3, on multiprocessor systems and parallel processing, the program order may or may not be preserved. We'll talk about that coming up, where you do that intentionally at the instruction level. It certainly can happen large grain size 2 problems tasks. And that depends on the memory model, and we have lectures on that too that we'll talk about. And then number 4, the determinism yielding predictable results can be controlled by a programmer as well as by constrained modification of writable data in a shared memory. So that we'll talk about when we talk about cache design with shared memory, the SMP, shared memory processing, symmetric multiprocessing, and cache coherency. And so I wrote a program inside of IBM to do that, and we'll discuss that in a later lecture. Now, what you see down here is a dependency graph, and in that graph, I've put a notation, actually made a correction over here to the textbook. But an arrow without anything on the arrow, any little circle or dash, just means no dependence. And then with a little circle means data or IO dependence. And then resource dependence is a check here, waiting for the resource. So you can see now the flow of things when it's rewinding here in the 2 cases above, when you're just rewinding the tape unit, and then actually waiting between S2 and S3, because you can't rewind between S2 and you can't write while you're rewinding, so you're waiting on the resource. And then the circle here is the dependence that we've talked above about the IO dependence, where you're reading and writing different arrays at different times. And then below here is control dependencies. And control dependencies, where the order of execution of statements can't be determined before runtime. So, for example, conditional statements like an if statement will not be resolved until runtime. So the different paths can be taken at different executions of the same code, conditional branches. And so, and then also, I have that case C.1 is the way I label it here. And then case C.2 is where dependence may also exist between operations performed in successive iterations of looping procedures. So we'll talk about this, or I've already talked about this when I talked about the research and the custom kernel and the APIs I made for our systems level testing, verification, quality control of the supercomputers, where we would have a combination of different controlled randomness, using different random number generators. Actually, my idea that they patented it inside 7 different random number generators for different reasons. And so we would randomize arrays of data and decision tree decisions going on, and we try to stress different hardware failures before it would happen for a customer. So we'd get repetitive thrashing with caches battling over a certain memory address, shared memory address. At the same time, there'd be a page fault, and having to reload off of storage, to main memory when you have a page fault, and try to make that happen over and over again. But there'd be different decisions made each time we're running the same program, because by design, and then we would run successive iterations, often of the same program, and in different when there'd be different loops nested inside. So when I saw this firsthand and was designing programs around this and because of this inside of IBM as part of the hardware design group that I was in and research group for System 390. Now, before we get into the details of scheduling parallel pipelines and superscalar machines and multiprocessors and looking at the interprocessor communication, we want to talk somewhat in the abstract, in a graph kind of way, about hardware and software parallelism. So with hardware parallelism, there's going to be a cost-benefit ratio because you actually have to build the and pay for and reproduce the hardware. So you want to know what you're getting for your dollars. And that's, of course, defined by the machine architecture and hardware multiplicity, and a function of cost trade-offs. And just for example, if you have a K way K K issue processor, that's referred to as a K-way or a two-way superscalar, three-way superscalar, parallel pipelines where you're doing fetching multiple instructions at the same time. And in addition to this, you're going to have out of order execution units. Now we're going to talk about later, and scoreboarding, because there's data dependencies between parallel pipelines. Sometimes will cause pipeline stalls and degrading performance. And another example of hardware parallelism will be multiprocessor, multi-core. Those are synonymous. If you ever hear me say multi-core, multiprocessor, even multi-computer networks, it's all kind of the same thing, just different interprocessor communication methods. So we essentially have computer networks in a box now. The MPP systems, massively parallel processing systems, are multiple processors, each with their own memory and their own caches and some kind of static or dynamic interconnect we're going to talk about, all in one box. And we're even seeing network type communications now, even in the SMP machines, with packetized serial communication, um, in the even in the PCs that you would see in networking between computers. So again, multiprocessing, multi-core, multi-computing is all kind of the same kind of thing, just different types of interprocessor communication. That's all hardware parallelism, and so we have to look at the cost-benefit ratio and talk about the limits of what we actually have implemented when we're going to analyze what we're doing. Now, software parallelism, it's up to the programmers. It's defined by the control and data dependence of programs, um, and it's a function of algorithms and programming styles, compiler optimization. So now we're going to look at a sample problem of A equals XY plus ZW, and simultaneously we want to do B equals ZW minus XY. So we have product terms and then adding and subtracting, and these product terms are in common to each of these equations we want to do simultaneously. So firstly, we assume that everything is available, all of our variables are available. We don't have to get them anywhere. This is a software ideal model. We don't worry about if they're coming out of cache, or if there was a cache misses or a page fault and it's not in memory and got to get it off the storage, or a million different, not a million things, but many different things can happen constraining that assumption. But in the software model, we assume everything's available. So we do our products here. We do the XY product that each of these equations has over on the left side, and the ZW on the right side. And then we assume we have them all immediately, and then we do the multiplication to get the products, and then we share that between the equations simultaneously. Because software, you don't have to worry about the communication, where that's coming from, where it's been stored on each side here. And then we do the addition or subtraction, depending on which equation, to get the A or B. And so that is the parallelism there. Parallelism as a quantitative term is equal to 8 over 3, because we have 8 uh, instructions, or 8 tasks actually here, not instructions, but 8 tasks. Well, actually, well, let's just call them tasks here. Well, they're instructions. So 8 instructions, per 3 machine cycles, right? And so that gives us a number of 2.67, which with no hardware constraints and ideal. And then we're going to look at two cases of different hardware. First, parallel pipelines in a superscalar processor, and then multiple processors. So first, we're looking at a two-way superscalar here. So two pipelines, but then certain restrictions on the hardware. So that down here it gives you those restrictions. So it says, now consider execution of the same program by a two-way superscalar processor, which can execute one memory access, a load or write, and one arithmetic, add, subtract, or multiply simultaneously. So there's only one ALU here, which, and that's not uncommon. And then the read and write operations, load and store, assuming maybe you have to get them out of memory, and you only have one pathway to the memory off of the CPU. Then that's, these are not unusual constraints, even in the fastest of processors. So what happens there? Well, then you have, you have to load over here, and then and all your loads are lined up because you can only do one at a time. So you're doing them over here. Now you can shift these around. You could try different ways to optimize this, but this, just the way it's given here. Load 1, 2, 3, 4, the four variables, and then once you have these two loaded here, then you have to have two loaded before you can do an operation. Then you're doing one of your arithmetic operations. You wait for the other two load, and you're doing arithmetic operations. And you see here these wasted resources, wasted space here, because this one pipeline has weights in it. It's not being flushed, but this is why we talk about out of order execution and scoreboarding later on, is and and scheduling here when we do it. And this is before we even do out of order execution. And so going on here now, you see the arithmetic unit there. It's doing the multiply for the product terms, and then there's a wait here while that multiplication happens, because you can't add. Now you need to add once you have your products, your two product terms for each of these equations. You can't do an add or subtract until the ALU is free, so you have to wait over here, and that happens. So you're doing your last of the multiplies for the partial product right there, and then you're doing the add, and then you got to wait because then you got to do subtract. And so you look at all that, and that is 7 different cycles, the same 8 instructions. And so now our degree of parallelism is 1.14 as compared to the 2.67. So we're going to do a couple examples of this, but first we're going to look at this same example by doing a multi-core, multi-processor system. So now we look at a second example comparing the original software parallelism to hardware parallelism with now a dual core, dual processor system. And in this case, there's inter-processor communication. And that can be different depending on the architecture. It may be that this data is being passed directly, maybe in an MPP system with a dynamic interconnect of some kind between processors, or it could actually be going through memory with all the latency involved with that of a shared memory system. So in either case, it needs to be considered here. And so in this example, we're constrained by not being able to do more than 2 loads or 2 stores in any operation, as stated above up here. And so, presumably each core, each processor can do a load. So they're loading, but each cycle is limited to only one one store per processor, so 2 stores per cycle, 2 loads per cycle. So you see the variables now coming in, and these are loads, so load, 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 load. So now these partial products, we're still doing these 2 simultaneous equations here. So we're loading the partial products that each of them are using, so they have to share them at some point. And so load, load over here, X and Y, load, load over here, Z and W sequentially, because there's only one load per processor core. And then the operation of multiplication happens on each of the cores or processors, and then they need to be stored now. There's a store here because you got to store them before you can load them onto the other system. So presumably this would most likely be an SMP shared memory system if you're doing it like this. But you still have some interprocessor communication delays even if you're doing a direct processor communication, because you have to usually do some kind of parity check when you're transferring information across, and some kind of semi-foring of, are you ready? Yes, here you go. And there's still delays, but this looks like it's most likely going to be a shared memory processing system with the stores and loads into memory and back and forth. That's how the things are getting to each other. And so they're loading the partial products from the other core or processor, and then finally doing the arithmetic operation of plus or minus when it has the partial products all together on either side, on both sides. So when we do the calculation for that, we see we have now 12 instructions divided by 6 machine cycles equals 2, which is better than the 1.4 for the two-way superscalar hardware of the previous example, but still not as good as the 2.67 for the pure software ideal case with no hardware constraints. So this is just, these examples are just one of the reasons you want to realize that multiple cores is not going to double your speed. Now, we talk about that, and scalability and Amdahl's law, and actually how to break that paradigm somehow now, or not somehow, but you do it. You treat your processors like network nodes, and then you don't have the same scalability problem. But nevertheless, you don't want to just assume uh, double cores means double speed, or 12 cores means 12 times the speed, because there's interprocessor delays, and you can see what's going on here, why there's these dependencies causing that. Now here's another example, and in this one I introduced a 5th variable, v. So the equations a and b now have what you saw in the last example of these xy plus zw and zw minus xy. That's the same, but now each of those is multiplied by v. So in the ideal case now, again, we don't have to worry about limited resources of hardware, so we just assume everything's available all at once, instantaneously and in parallel, and all 5 loads happen simultaneously. Now, the V needs to just sit there. We could actually wait and load it a little later if we wanted to. No reason to not load it here in the ideal case. And these these product terms are formed just like in the previous example. The XY, it's in both equations, and the Y and the WZ, ZW. And then those product terms are formed, and then they need to be shared, and they are instantaneously here in the ideal software model to do the plus and minus simultaneously of these quantities. And now everything can be brought together with the V multiplication, the V times all this, V times all this here. And then I've also added now the option, in addition to new equations, the option that results loaded into memory. So we have 2 different things we can calculate here. These 11 instructions divided by 4 cycles would be 2.75 parallelism, in this case the ideal software parallelism, and or 13 instructions, because these 2 more stores to memory, divided by now 5 cycles, extra cycle for storing, and so that's 2.6, still software parallelism with no hardware constraints. And then here's an example with 3 pipelines now. And so you have these resources, and we'll see in scheduling we can optimize this. This is, there's different ways of doing this, especially when you have all kinds of parallelism. And there's ways to optimize that, including the out-of-order execution and the scoreboarding, which we'll talk about later. But first, we'll look at just scheduling and how we can move things around. But in this case, let's do this. We'll load everything into one process or one pipeline here, and then do, just ignoring the fact that this one's open over here, and do our computations, because we only have one. Our constraint is we can only do one load or store at a time. That's fine. You say, well, you could load over here, but we only can do one arithmetic or one arithmetic operation per cycle. This is a single processor, just multiple pipelines. So you're going to have to wait no matter what. And so here we load, and then do an arithmetic, load, do an arithmetic. And again, you could probably pack this a little tighter, but just in this example, go with this, and then we use the V here, and again, we need the ALU for that. And then lastly, we store. So assuming this is optimal here, or even if it isn't, just for the sake of this example, allow what's here. And we have 11 instructions over 9 cycles now, which is 1.22, which is not good. The bigger the number, the better. And 1.3 if we do the store, because then there's 2 more instructions and an extra cycle. Now, in this example of hardware, we have dual processor or dual core. Each of them are not superscalar, so there's no parallel pipelines in each. And each processor or core has the constraint of only one load or store memory access and one arithmetic instruction per cycle per processor or core. So what we see here, it's very similar to the previous case, although we have the addition of loading the V value in these new equations. And we still have interprocessor communication, and then we have the option of storing in each here. There is one thing to note here. We're doing a load over here and an arithmetic over here, which is perfectly fine since that hardware is available. In this case, we get 16 instructions over 8 cycles, is 2 for the hardware degree of parallelism. Or if we add 2 instructions and 1 more cycle, we're still at 2 for the degree of parallelism. Doesn't mean the execution time is exactly the same, because there's more cycles here. So we need to distinguish that. And we'll see that in the scheduling that we'll do in a minute. And then in the table below here, you see a comparison of the ideal versus the superscalar versus the multiprocessor, multi-core, with the option of storing. And we see that although the multiprocessor has overhead of inter-processor communication, it is closer to the ideal. So bigger is better here, so the 2 for the multiprocessors here. And the ideal is up here around 2.75, 2.6, where the superscalar is lower here. 3-way superscalar, due to the rigid constraints, wastes resources at different cycles here. You can go back and look at those, and wastes an entire pipeline that's not being used, and so therefore would be really the same as of a 2-way. So more is not necessarily better here in terms of how many pipelines if they're completely underutilized or not utilized to their fullest. So we need to do a number of things here. First, with scheduling, without out of order execution or hardware scoreboarding, but with just regular scheduling, that we'll see ways of optimizing the number of pipelines or number of processors and for given tasks. So from those examples, we can see that there is a difference always between hardware and software parallelism, where software is the ideal and then hardware creates constraints. And to address the difference, certainly can do better hardware, which we are talking about already, and we can see. And then the compiler also will help with that. And so we're going to get into now some scheduling and the static, also dynamic scheduling and out of order execution. But first, we're going to do some grain packing and scheduling and partitioning first. And before that, we just want to talk about the type of problems that arise and how the grain size and latency comes into play. So grain size has to do with the type of problem. We'll see a diagram of that in a second with fine, medium, and coarse grain. And latency is just a delay, communication overheads and synchronization latencies, how many times you go to memory or if you're going through caches. And so now we see this diagram that shows grain size with coarse grain. Um, you can zoom in here, but there's details. I'll just summarize that you have coarse grain up here and small grain down here. And so there's a higher degree of parallelism that's required to deal with the fine grain and also uh, increased interprocessor communication, the IPC, having to deal with all that. And so we see if we have a job or a whole program is the coarsest grain, and then subroutine, subprograms, or subprograms, subroutines, then loops, and then the instruction level parallelism. And an example of this fine grain would be matrix and vector manipulation calculations, linear algebra. So in matrix multiplication, you have a row times a column, and then you sum the different elements after you multiply each row element times a column element, and then sum them. And that is shown here. You can see the matrices here. This is just adding two or multiplying two matrices, A times B is row times column. And that is a dot product in vector terms. And you can just see that detailed here. Um, and that is the finest grain and can be the computationally most expensive thing to do often. But certain kinds of hardware are uh, made for this. The vector register hardware, the Cray systems were some of the first. At IBM, we came out in the mid 19 or didn't come out then, but when I worked at IBM in the mid 1990s, we had a vector register unit we patched onto the System 390s, and we could then do vector register operations. Um, and so that's all it says down below here is that this is this is very communication intensive unless special hardware created to do this vector register hardware. Um, and then it just says vector register. Computers have special multiply accumulate instructions to do row times column operations. Also, it's worth mentioning that neural networks lend themselves to this kind of thing. Also, That's a vector register kind of operations, fine grain coarse or fine grain problems, and there is special neural network hardware to do that. And one of the two processors that I made in the beginning of the 1990s was to deal with just that kind of thing. And actually, both were, but the one was more of a biologically modeled spiking neuron, with, different than the traditional neural network processors in my first one. So, hardware and software parallelism and DOP, degree of parallelism, are models. So to initially design and analyze hardware and software. So we saw that saw that here, or up above. We did the ideal software case and the superscalar case, and then an SMP multi-core, multiprocessor case. And now we're going to deviate from these models to look at real code and real hardware, where what actually happens in different pipeline stages, the fetch, decode, execute, is not so standardized as to fit these DOP type models. So we need to drill down a little deeper now to see what's going on. And then, for example, and we'll look at a couple of these coming up. For our SMP, it looks like this with a memory and shared processors. Also, SMP is where we have caches between the processors and the memory. So we have to deal with that. And we have a whole couple lectures just on cache design, and there's multiple layers, and there's interleaved ones, shared ones, dedicated ones. There's lots to that. And then we have two MPP models here I've drawn, is where each processor is alone on its own, doesn't share a memory, has its own memory. And then another example, which we're going to look at, of an MPP, is where the processors, where the memories are actually talking directly to each other through a DMA, direct memory access, and freeing up the processors. So that's a whole different thing. And then this just says over here, and IPC and interprocessor communication may not always be as easily modeled as in the abstract, the graph diagrams, the DOP models for our SMP in the last lectures, or the above part of this lecture, using loads and stores. So it's, I guess, a simplification you could say up there. It's still valid for your initial concepts, but once you drill down into your scheduling and affect your hardware accordingly in your hardware design, then you look a little more detail. Okay, there's quite a bit on this slide here, and I need to explain this whole format. The way this looks is because I taught this course for a couple of decades now. Used to write all this on a board, on a chalkboard, and then I'd add overheads long ago. And then I published a collection of notes and book excerpts in the bookstore for the students to buy, instead of asking them to buy several textbooks. And then I've scanned all this in and made PowerPoints out of them, and now save them as embedded audio PowerPoints, and then save as MP4s and upload to YouTube. And if you want to zoom in here, you'll need to maybe look at a link if you're on YouTube for the PDFs, and then you can zoom. It's a little trickier to zoom with watching a YouTube video. So now we're talking about grain packing here and scheduling. So really getting down into the nitty gritty. Now there's a problem we're going to look at, which has 6 loads and 1 calculation per processor at a time. And this is not superscalar. This is there are 2 processors in SMP configuration sharing memory. And we want to establish a notation. Also inside the processor, we have an ALU, and we're doing register to register computations. That's also an assumption here in this problem. And then there's establishing a notation. So you're going to see 3 different kinds of instructions here. You're going to see memory reference instruction over here, and then immediate, different addressing modes where you're accessing memory versus your data is immediate reference instructions, data coming in with the instruction when you fetch it, and then a mixed mode kind of thing over here. And so looking at the notation here, I won't put the cursor over the top of it, but reading what it all says right there above is given you have a memory reference instructions only loads here. And it takes 1 cycle to address, 6 cycles to read from memory. So the notation is the 1 cycle, the address is that 1 there. The number is just the number of the instruction, and then 6 cycles to do a read from memory, and that's going to be represented as an output, comma 6 for 6 cycles of delay. And then example here would be code number 2, b equals 2, and so then you would have b comma 6 for the output is b equal 2, and then the delay is 6. And you consider the grain size of 1 as a cycle time. Over here now is a immediate reference instruction, and with the node number again divided by grain size. And then you have the input that's causing that's resulting to being here divided by the, or not divided by, notation over the delay, and then the output over the delay with that. And the data comes in with the fetched instruction, and takes 0 cycles to get that data because it's come in with the instruction. And so we see that actually down here on this notation here. This is a mixed immediate reference, register reference instruction where there's 0 cycles delay here, right there. So what we see over here, if you zoomed in, it would be 3, comma 0 on this arrow coming in here, and as example code of for instruction number 14 in the code would be n equals 3 times m, where the 3 is actual input coming in to this node, to this instruction, and then it's going to be multiplied by m, which is represented coming in on this other arrow here, and then the output is n, so it's n equals 3 times m. 3 times m is what n equals, and it's instruction 14 here in the circle, comma 2, and that's because that instruction takes 2 cycles to complete the arithmetic instruction. That can have special I/O delays associated with it. That's what that says. You can see that down here. Now, what we'll do in the classroom is I'm just going to play this video, and then for the students' sake, we're going to go into the PDF and zoom in and go back over everything. If you're reading it at home, of course, it's on YouTube. If it's just for fun, go on as fast as you would like. But in the classroom, you probably need to go back and take a look at this and before we move on, get a feel for all the notation and the code and how it's symbolized. Some notes here. This simplified SMP, shared memory symmetric multiprocessing system example has no memory reference CPU operations. So in a traditional RISC sense, you want to get everything into the CPU and just use the registers. Although in reality, you're going to have cases where that's not the case. But in this example, that's what we're doing. And so, the math operations are not any, there's not any memory reference, they're just register reference. Also a note, although this is an SMP machine using memory for interprocessor communication, no separate loads and store instructions like we saw above in our examples above, when our hardware and software parallelism comparison. And instead, we're scheduling and using delays. So the delays, that interprocessor communication is showing up, in the arrows. Uh, Up above, we needed to account for it in the hardware degree of parallelism with multiprocessors with separate cycles, that we were counting for um, just for interprocessor communication for loads and stores to memory. And that's just implied to be going on here, that kind of thing where you're talking through memory, this SMP machine. So the only way the processors have to get information to each other, except if we were doing DMA, which we'll see in another case, which we're not here, is to go through memory. And so now what we see here is a list of all the instructions in the code. Um, and these are memory reference instructions, and these are our loads. And then we have CPU instructions, and they're not memory reference instructions here. And so we're assuming just working with the registers. And so the memory reference instructions, as stated above, just are one cycle to complete. So these will just take one cycle to complete. And then all the arithmetic here take two cycles to complete. And then there's delays involved here, as will be shown on the graph. So the delays involved with the different ones. And now these are given to us here, and these are I/O delays. Um, and we're just taking those, assuming those are accurate for each of these computations here, depending on what's going on. And then we have the type of grain or the type of grain I/O delay, data memory read latency, says here, and here it says IPC or unspecified. And so that is a given thing for this problem. Again, you want to take a look and stare at all this before we move on to the next thing. So the steps to this problem will be. So now we want to lay out everything, all of these instructions, without really paying attention to putting them in layers here. This is just for organizational purposes. It looks like two cycles. But these are all the loads. These are all the arithmetic. And then most importantly, starting to find dependencies and the paths, and how many arrows it takes, to get to whatever point you are along this graph. And so we have all the loads up here and all the arithmetic down here. That's just how I've organized it. But again, it could be sideways here. I mean, it's an initial draft. And then we want to find a critical path. Now, the critical path has to do with finding the least amount of arrows between, least amount of jumps between. And so we're making an assumption here. We're not looking at exact delays on each path because they're approximately the same order of magnitude, pretty close. But we want to just add the number of jumps that are between getting from one node to another and to another down paths. And we want to look for a critical path, and which means whichever has the most jumps. Now it turns out to be four different cases of the same amount of jumps, and so we pick one of those as our critical path, assuming approximate equivalence there, and then we want to begin to group the code on one core to begin executing this critical path as soon as possible, and do first CPU instruction as soon as all 6 loads are done. So then what we have here resulting is a coarse grain from these fine grains here, but 4 and 6 we're using for 11, which is a computation arithmetic operation. And so that 4, 6, and 11 will be our first coarse grain A, assuming all the loads are assumed to be able to be done simultaneously, which is part of the given problem, that we can actually load all 6 at once, which is not always a common thing, but in this case it is what we're given. And then we want to go on and make more coarse grain. So we just made coarse grain A. We're making coarse grain B and C. Um, and um, and you want to find groupings of other fine grains into coarse grains to maximize concurrency while minimizing delays. So go back and look at the original graph with the delays, the sketch, and the first step, and then uh, make coarse grain A, and then coarse grain B, and coarse grain C. And it makes sense to do these two simultaneously as two separate coarse grains on separate processors, cores, because they both only need data reads from the first simultaneous 6 loads. And we do that after A, coarse grain, and then do coarse grain D. And so you need to do that, or you have to wait to do that before after B and C because it needs coarse grains B and C. And group these because 14 and 13 um, only need immediate data. Then we make our last coarse grain here E because all fine grains in this coarse grain need results from other coarse grains B, C, and D. And then we put everything together in a coarse grain map. And as you can see here, it's everything we just did above from the initial sketch of all the fine grains are now grouped into coarse grains, and the cycles are adding up because it's accumulation of all the cycles of the fine grains inside, and then all the delays and the outputs and inputs are shown on the graphs here, on the arrows of the graph. So you make a coarse grain map. So now we're going to do scheduling, and what we're going to do is we're going to, on our two processors in our SMP system, we're going to put all of our fine grain instructions that we have on over here, and then we're going to do coarse grain here, and we're going to compare and look at what the speed up is of how long it took here divided by how long it took over here, and that's our speed up. And it's not instructions over cycles here like we were doing before in degree of parallelism. This is a speed up of what we did before um, here divided by what we did now. And so if we reduced it's a smaller number of what we're doing now, and you put that in the denominator, then the overall quantity goes up. So your speed up goes up. And so we have here M equals memory latency for read, IPC equals interprocessor communication. Um, Star is given for problem as an output delay, but if on the same processor, you could maybe be eliminated with other architectures in a process. Okay, so you can see in these gaps here what's going on, memory, IPC, the stars, idle time here. Idle time, it could be used for other tasks too. It's just kind of wasted time, but could be used. And so, look at these two. Now you can, this is a hand calculation. You can reorder these yourselves and maybe find a different combination for, both sides here and show a different improvement. When we do dynamic scheduling, we'll see we do out of order execution, and there's methods for that we'll discuss. And then there's also now methods using neural networks to actually do some of that. So yeah, you look at these two, fine grain, coarse grain, packing the grains, and then seeing if there's a speed up. And we do have, in this case, 1.11. If it was just 1, there's no speed up at all. But it's greater than 1, so there's a speed up. And this is the same example just out of the book. So if that didn't make sense and you want to look a little more at something else, I'm going to leave my original notes up here, and you can see the packing. And it's nice to look at this diagram here. You see the fine grain and the coarse grains. And so you look at the two of them, and then the code. And all this here is saying the same stuff. It's all the same as above. I just redid it in my own words, but sometimes it helps to look at two different things. And again, all the same here, and you can zoom in on the PDF and see the tiny little print that's probably hard to read on the YouTube video. without the ability to zoom so easily. Same problem, just in the book notation. Now this is something different now from the book. I mean, it is the book is showing something I didn't draw out separately. And what you see here is using a node duplication. So if you have some idle time, you might as well fill it with something that maybe helps you reduce reduce the overall scheme of what's going on here. And so there's no duplication here, like that thing that I showed you on the right side of that slide above in the first coarse grain. This is coarse grain, right? These are coarse grains. But over here, where if we put in the slot the idle time over here, we put a duplicate of the coarse grain A, that's going to have a result of a speed up. And so we compare this before to the after. When we take the before, which is slower, divide by the after, we see a speed up now of 1.93 just by using node duplication. And then here's a summary. Of the steps is construct a fine grain program graph, schedule the fine grain out computation. Number 3, grain packing to produce coarse grains, the graph for that, and then generate a parallel schedule based on the packed graph. And it's implied that you can do the node duplication as part of that too. It's a 5th step, but you could note that way if you like. Okay, now we have another problem, and this is going to be a matrix manipulation, matrix computation problem where you have matrix A times matrix B equals matrix C. We're not going to use vectors here. This is just looking at multi-processor systems, actually going to be an MPP system, and comparing a single processor to the use of 8 or 4. How many processors does it make sense to bring in to use? Doesn't mean you're going to change your entire hardware. Just looking at how many processors does it make sense for this particular problem. And so, again, here's the problem that's given is here. And then we also want to sum them. So it's first we're doing this matrix times a matrix equals this. So again, that's a row times column operation. Row times column is that first element in C, and then row times column. There's 4 different dot products to come up with the C's in the final matrix, and then a second computation after this matrix computation of just summing all of the elements in C. So it's a 2-step process. And here we want to calculate both speed up and average hardware parallelism. And using here as an assumption just 1 operation cycle per instruction, not clock cycles. But we're doing 2 things. For both degree of parallelism, like we did in the very beginning, hardware versus software, and speed up from using 1 processor versus 8 or 4. So the first thing is to construct a fine grain program here. And this is the actual code. And this is assembly language code. And this is Motorola 68,000, which I've tell stories about in other courses. And Motorola is a fine company. The 68,000 was in all the first Apple computers until they went to Intel processors. Also in the very first HP calculators were the M6800s, and I had one of those 40 years ago that I paid a lot for just to program 42 years ago. And there's a fine assembly language. I teach assembly language. This is what we're looking at here for the fine computation that's going on for A times B, and then the A times B's for the different, and then adding them. So an A times B here to get this, and then adding the different things because they're dot product, row times column. It's like this row times this column to get that element is this times this plus this times this, right? So that's how you do the vector operation that's inherent in the matrix operation. Is a dot product. And so we look at the code and the grain size and the cycles. You have to go down and drill down and look at the machine and cycles. That's why you need to know some assembly language and understand the cycle times involved with different instructions and how computationally expensive, relatively speaking, each instruction is compared to others. And in other courses, we do this comparing microcontrollers to microprocessors. And you'll see that the more powerful instructions are great. You need less lines of code to do a given task, but if you use like a simpler device like a microcontroller, you're going to need more instructions, but each instruction takes a lot less time, so you could actually have a net benefit. But anyway, that's for another topic, another course. Most of my students will know what I'm talking about when I mention that here. Then next, we want to go down. Oh, well, we want to calculate communication delays now. So this is tricky to look at here. This, you say, well, wait, what's going on here? The processors are talking to memory. Well, they each have their own memory and they have their each direct memory access. And I say, recall from other courses, lower level courses, that direct memory access is where the memories can talk to each other directly, and that frees up the processor, so it's not involved in the communication. And so, it's unlike an SMP, symmetric multiprocessing, shared memory processing, where the memory, the processors have to talk through memory. Here, this is a direct memory access here. And there's a time delay here. They have the cycles of 212. Cycles is your time of your interprocessor communication delays. Then, once you have all that, you make a fine-grained program graph, just like we did in step 1 above in our fine grain, and you take all those delays and you have all the multiplications here and the adds, and then finally that second instruction where you're summing all the different elements up. So we're doing that here. And then down here, I have a notation here for this, that we're doing an MPP machine, massively parallel processing, or a computer network. But that note, although this is a type of multi-computer system, multi-processor, multi-core system that we are calling an MPP, most common MPPs look more like this. So you would have more of a dynamic interconnect crossbar switch. We did this at IBM, connect a couple different $1 million machines together, each of them with over 500 processors and other things too. You could hook up a Cray supercomputer and a Sun workstation network and a PC network, all through this giant optical, it was called parallel sysplex optical interconnect, using optical channels. And so, super high speeds you can get with your optical cables and channels. We were doing that in the IBM in the 90s. So here is the solution to the problem stated above, which is a matrix multiplication and a summation of all of the elements in the resulting matrix. And it's done on an MPP machine with direct memory access between the memories, freeing up the processors. And then there's an IPC, which is relatively expensive, as it always can be right there. And then the very fine, super fine grains for each of the fine grains, the multiplies and adds written above in assembly language, Motorola assembly language modules. And then firstly, you should always look at the ideal degree of parallelism. And so when you make a fine grained graph, you see what that is with no hardware constraints, entirely software. So that's 3.75. That's the ideal case. The degree of parallelism gives you a conceptual idea of what's going on. Then you schedule things to see actual speed up. So, and then the first case is a single processor, single issue, meaning not superscalar. And so everything must be done sequentially, and that's the most costly. And so that's going to be our worst case for our degree of parallelism, and also for our time that we're using as a reference for speed up. So everything will be with respect to that. When we do 8 processors, 8 cores over here, and then we look at how that's going and all the loads here on separate processors, which you can imagine is probably not going to be the best thing to do, but until you actually do some kind of thinking about where the IPC is and the dependencies, you might do something like this. So you have now 8 loads going on at the same time in different processors. And these are all single issue processors, so there's no superscalar within each of these processors or cores. And then you see the speed up there with respect to the worst case. And then we do grain packing, which is when you are thinking about how to cluster together coarser grains of execution of different fine grains, putting your multiplies together, your dot products of creating your row times column for your matrix manipulation. That's making different elements in your resulting matrix. And then scheduling those coarse grains on here and also accounting for IPC, and then calculating your DOP and your parallelism as well as your speed up with respect to your base case, worst case. And then we look at all those here, including the ideal parallelism, and we see and compare those, and we see that doing 4 cores with some kind of grain packing in this problem is the most optimal thing to do, and then some conclusions about all of that, and what you need to do to consider wasted resources and optimal scheduling. And if you redo all 3 cases, the single processor, the 8 processors, and the 4 processors, with allowing each of these processors to be superscalar, two-way superscalar, then you're going to have something like this to look at for scheduling. Now, in this example, it's a little simpler. This is just a simple vector dot product, not an entire matrix manipulation, matrix multiplication with a number of dot products involved, row times columns. And it's a little simpler. And then the grains are not super fine here. I'm not breaking down into the motor roll. I'm just saying that each multiply and addition is the fine grain, as well as I've added loads and stores on here. And so now we're going to do a ideal case again, or do the fine grain graph, ideal case of degree of parallelism, and then again doing a single processor, not superscalar, and that's going to be the worst case for degree of parallelism, as well as the worst case timing that we're going to use as a reference for speed up. And then we're going to do, in this case, in this example, a 4-way superscalar, not 4 cores, but 4-way superscalar. These are 4 parallel pipelines within one processor, 4-issue, 4-way superscalar. And we see how that works out. And then we're going to do a 2-core single issue cores processors, and then with grain packing too, and then adding a couple IPC processor communication loads and stores for them to talk to each other. But small, intentionally small values, just to make a point here. And then we look at all this again here, and we see that even with the very small IPC, the very small interprocessor communication, that the superscalar parallel pipelines is the best case here. And then the conclusions here says that, as well as even if we simplified the 4-way superscalar down to 2-way superscalar, it would still be better. The superscalar is better sometimes. So the problem's not complex enough to lend itself to parsing into a number of different grain packing on different processors to get any efficiency on this scale. But it's a little simpler to follow this problem than the last one. Now that we've been talking about interprocessor communication, IPC, and the costs of that, we want to look at a case of these GPUs, Nvidia H100, H800, and H20, where the interconnect bandwidth is critical in the large matrices and the neural network computations that are used for deep learning in these Nvidia chips, GPUs, graphics processing units originally designed for graphics processing, but because of the nature of the type of data that they deal with and the architectures, it lends itself to the linear algebra intensive computations involved in deep learning and neural networks. And so we see here the H100 chip is the highest performing at the moment, both in interconnect bandwidth as well as computational performance. And that was banned by the Biden administration, export controls to China in 2022. They did get a hold of a bunch of them, these H800s at that time before the Trump administration recently banned the H800s. And then DeepSeek for tens of millions of dollars compared to the tens of billions of dollars that was typically used to make the large models, complex reasoning models out there. And they did that by using a mixture of experts and some distillation methods, as well as some other techniques that I will elaborate on a little bit in a minute. So DeepSeek, a Chinese company, actually a spin-off of, I believe, a hedge fund, but with not a lot of people, and claiming only, I believe, $60 million instead of the billions and billions of dollars that was used to make the more sophisticated models. Use the chips that were banned, plus their creative techniques of mixture of experts and distillation methods and some other methods as workarounds. And when they released that information, it almost crashed the market. We're having other troubles right now because of tariffs. But this was when the announcement came out about a way to cheaply do some of these complex reasoning models, deep learning models, much cheaper, which seemed to run in the face of billions and billions of dollars being planned for new data centers and governmental initiatives too. Here you see a quick Google search and the AI response to how did DeepSeek do what it did so inexpensively. And then I've highlighted a couple things here, including mixture of experts and the distillation methods. You can read that. So here is what a mixture of experts looks like, essentially turning off parts of the extremely large neural network and only using parts that are relevant. This was a wish list 35 years ago because the neural networks were never of this scale. I had talked about this in my master's thesis, actually, but in 1992. But it wasn't until now where this is very much relevant in saving computation time and needed hardware by only having part of the neural network fired up, both during training and inference. And here I will let you answer this question. If DeepSeek unfairly used OpenAI and ChatGPT to help train their newer model, and that OpenAI spent billions of dollars, many billions of dollars, and then DeepSeek used that to help train its smaller model. So when they claim, it only cost 60 million, you have to consider that something came before that, and they used that. And then they make their model open source. So I'll let you decide on how you feel about that. But it's speaking to some of the latest trade restrictions, export controls, where now even the H20, we'll see in a second, is being banned, kept from China. Here you can see some of the details of the Nvidia H100 GPU, and we're going to focus on one particular aspect of it is the communication bandwidth, which we were just speaking of, interprocessor communication, and in this case, We're going to look at the PCI Express and how that is used. So this slide is focusing on PCI Express in the H100, the most high-performing of the Nvidia chips for both floating point operations as well as connection bandwidth. And this is the connection bandwidth means is PCI Express, which is parallel serial lines. So a number of years ago, that was a major paradigm shift in computing to go from parallel communications to serial, and that involves packetizing the information, having beginning and ending eliminators, and dealing with packets and then unpacketizing for computation. And there's links to my lower level lecture on that. So here's some more detailed analysis from this peer-reviewed publication on these Hopper series, the H series, with the H800 here in this column, and looking at the performance changing from the previous generations, the A series, up to these Hopper series, and then the 800, which is not the highest performing, not the H100, but it gives you an idea of the change in performance in recent years. And most recently, we have here export controls now in 2025, a couple of days ago, on the H20, which, as you can see, is not as high performing computationally as the H100 or the H800, but it has this interconnect bandwidth, and because of the recent workarounds by DeepSeek and many people following after that now to do distilled models, this is now a powerful chip in the eyes of the present United States administration, and is now falling under export controls. So Nvidia stock lost quite a bit in recent days because they had already planned orders for China to be able to use these that were allowed until just a couple of days ago. I believe $5 billion worth. So now we want to talk about dynamic scheduling and out-of-order execution. Now, this is not super new thing. We did a bunch of this in IBM and the large-scale systems in the 90s, and it dates back, I believe IBM was doing it in the 1960s too. It hasn't until recently, at least or in this millennium anyway, found its way into processors, common processors. So the idea is you want to order things such that the instruction execution, such that you don't have these waits for things because of dependencies between. You're essentially eliminating data dependencies by seeing it ahead of time and not executing things that are going to cause pipeline stalls or some instruction waiting for some other instruction to get done. So example dynamics scheduling using Tomasulo's algorithm to facilitate out-of-order machine instruction execution. So you'll see that in this example here, play this video in class, and then we'll discuss this, that the add operation in the reservation station, we'll talk about that on the left, will execute before the divide instruction on the reservation station on the right, even though the divide operation is first in the instruction sequence that you see over here. This is because the divide operation requires 40 clock cycles, to execute, whereas the add instruction only 2. And so those of you who've done digital design things with me and you understand the complexity and assembly language, the difference between a simple add versus a divide. Then this is a more detailed lecture, and actually part of a lecture series that it's a little bit longer but a little more in depth and on the same thing. And you can look at that. We'll play that, or at least part of that in class, and discuss that. It's certainly a very good lecture in itself to listen to. I highly recommend it. In this video, we're going to take a look at scoreboarding, and specifically in here, this is a long lecture also, but we're going to look specifically at these ready bits. And finally, here we see and listen to and discuss in class a video about using neural networks for prediction. It's not brand new. It's been around for a couple years now, but it's certainly um, in the 20s, 2020s and teens. Uh, and so watch this, and this is for using a neural network to predict. So as most of the students in here know, I designed 2 neural network chips in the early 1990s and won an award paper discussing, comparing them, and I teach a whole course and lectures on neural networks. So, but they're not in here in this class, although we will often design vector register and neural network transfer function kind of hardware in the advanced class like this one. But this lecture is not in my neural network per se class. But it's certainly worth noting that now neural networks are being used in mainstream processors. We were doing, out of order execution things at an IBM in the 1990s, but we weren't using neural networks then. So this is a recent thing.